A single endpoint call jumping from 50 milliseconds to 1.5 seconds is the N+1 problem manifesting in production. The root cause is a seemingly innocent loop iterating over a collection, triggering a new database query for every iteration. If the collection size is n, you execute N+1 queries instead of just one. This pattern bypasses the efficiency of relational database indexing and connection pooling, leading to connection saturation and massive input-output overhead. We are not talking about slow queries, we are talking about query volume explosion. This is the silent killer of application performance, especially under moderate load, rapidly exhausting database resources and connection limits. Start by enabling detailed query logging at the application layer, not just the database server. Use ORM-specific tools like Django Debug Toolbar or the Rails Bullet Gem. These tools count executed queries per request and flag suspicious patterns where multiple identical queries run sequentially. For production monitoring, integrate application performance monitoring tools like Datadog or New Relic, specifically looking at the database transaction trace. A trace showing hundreds of tiny, fast queries instead of one large, complex query is the definitive signature of N+1. Focus on the total number of database round trips per request. The primary fix is eager loading, which retrieves all necessary related data in the initial query, eliminating subsequent lookups. In SQL terms, this translates to a single join operation. When fetching a list of authors and their profiles, use a join to retrieve both datasets simultaneously. This is implemented in ORMs using methods like select_related. Select_related typically handles one-to-one and foreign key relationships efficiently by performing a single SQL join. This method is optimal when the relationship is mandatory and the related data is relatively small, avoiding unnecessary query execution overhead. Standard joins can lead to massive data duplication when dealing with one-to-many or many-to-many relationships, inflating the result set size unnecessarily. This is where prefetching comes in. Prefetching executes two separate queries, one for the primary objects and a second query to fetch all related objects using an in clause based on the primary keys. The ORM then stitches the results together in memory, avoiding the data duplication overhead of a large join. Use prefetch_related for collections and reverse lookups, ensuring the database only returns the necessary rows for the related entities. After implementing eager loading or prefetching, always analyze the resulting SQL query plan using explain-analyze. Verify that the database is utilizing appropriate indexes on the foreign key columns used in the join or the in clause. If the database performs a full table scan on the related table, the N+1 fix might only shift the bottleneck from query volume to query execution time. Ensure the foreign key columns are indexed and that the statistics are up to date for the query planner to choose the optimal path. A poorly indexed join can be slower than the original N+1 pattern. Even with eager loading, you might retrieve entire rows when only 2 or 3 columns are needed. This increases network latency and memory consumption on the application server. Use specific field selection methods, often called only or defer, to limit the columns retrieved from the database. For example, if you only need the related user's ID and username, explicitly select only those fields. This reduces the payload size significantly, especially when dealing with tables containing large text blobs or unnecessary metadata columns. Minimizing the data transfer size is a critical secondary optimization step. If the N+1 pattern manifests during data modification, where a loop iterates and performs individual updates or deletes, the solution is bulk operations. Use bulk_create, bulk_update, or similar ORM methods. These methods compile the individual operations into a single optimized database command, drastically reducing transaction overhead and round trips. For instance, inserting 1,000 records individually requires 1,000 database calls, while a bulk insert requires only one. This is critical for batch processing jobs or data ingestion pipelines where thousands of records are processed simultaneously. For highly repetitive, read-heavy lookups that are difficult to eager load across complex service boundaries, implement a localized caching layer. Use a Redis or Memcache instance to store frequently accessed related entities, keyed by their primary identifier. Implement a cache-aside pattern. Check the cache first, then fall back to the database. Ensure proper cache invalidation strategies, such as time-to-life expiration or explicit invalidation upon related object modification, to maintain data consistency. Caching should be reserved for data that changes infrequently or where eventual consistency is acceptable. The N+1 problem often reappears during refactoring or feature additions. Integrate automated query counting into your unit and integration test suite. Tools like Django's assert num queries or similar framework-specific assertions enforce a maximum query count for critical endpoints. If a developer introduces an N+1 regression, the continuous integration pipeline fails immediately, preventing the performance degradation from reaching production. This proactive approach is the only reliable way to maintain long-term performance stability, ensuring that query volume remains predictable and controlled across all critical paths.